Good evening. Good evening. We have a few more chairs that are going to be brought into the back of the room for the folks that are still standing, but let's get started. Good evening and welcome to the Explorers Club. My name is Paul Tangy, and on behalf of the Explorers Club, our Public Lectures Committee, our co-chair, Natalie Cash, who Natalie is in the room somewhere. There she is. I'd like to start by thanking you for joining us here on the snow day in the middle of the snowstorm here at the Explorers Club. Since 1904, our club has come together to form a community promoting the scientific exploration and conservation of land, sea, air, and space. And since 1922, every Monday night, we've gathered for a public lecture as part of our core mission of science, education, and service. Your presence here tonight makes you a part of this community. Your support tonight makes this tradition possible. And so for this, we thank you. Please raise your hand if this is your first time in the Explorers Club. That's fantastic. Welcome. You belong here. Please raise your hand if you're an Explorers Club member. Okay, to order a drink at the bar downstairs afterwards, please find one of those members to bring you as a guest. Our plan for tonight, here's our plan for tonight. In just a moment, I'm going to introduce our speaker, who will share this fascinating project for approximately 50 minutes. I hope you've warmed up your vocal cords. You may be asked to participate towards the end of this. Afterwards, we will have questions as well. I just want to start, though, by noting that as we look, or inviting you to look around the room and look at some of the artifacts that are around here. Peary's sledge, the flags that have accompanied expeditions, like the flag that went on the expedition that you're going to learn about. We're going to be talking about Greenland. There's an American flag there that was gifted to the club by someone who's in the audience tonight, Peter Neal. Peter Neal is a South African who circumnavigated the world with that American flag and with that ideal of America with him on his journey, and he brought it back to our community here. That ideal of a community, that science should be something that brings peace to the world and brings us together. You're going to learn about a really cool artifact that's sitting up here as well. But the artifacts only matter because of the people that are behind them on the expeditions. It's the people behind these artifacts who make the Explorers Club, who come back from their expeditions changed and wanting to support each other in that community that results from an expedition. And so it's really special tonight for me to look at the members of this expedition, to welcome you all specifically here tonight to this Explorers Club. They are led by their fearless leader, my friend, and my boss, Professor Britney Schmidt. So without further ado, please welcome Professor Schmidt.
Thanks, and I'll point out mistakes as we go through the talk as well. The first being that we caught all of the mistakes except that I have the wrong title. The theme for tonight is Tracing Warm Lines, which comes from a sea shanty. And we're going to talk to you about the warm lines through the ice. And there's a whole bunch of people that make that possible. So thanks very much, Paul. Paul was one of the folks on our expedition as our large mammal specialist, polar bear guard. But I wanted to introduce the rest of the team as well. So we'll go ahead and pass this around.
I'm Matt Meister, Brittany's lead engineer.
Hi, I'm Brandy Revels, program scientist, climatologist. Hi, I'm Frances Bryson, a research engineer.
Hello, I'm Henry Wolf. I'm an engineering student.
Daniel Lean, also a research engineer.
I'm Veronica Hageline, and I'm a PhD student.
Hi, I'm Jorge Gopi Masanet, and I am an engineer and a PhD student.
Awesome. So as we go through the talk, we're also everyone's going to get a chance to present part of the story. So look for those guys, and then hopefully you've met some of us talking about the robot and the data beforehand. We'll be around after the talk until they kick us out of the place. So please come up and ask us questions. I have a limited number of stickers, but I'll give out all the ones I have. And then if you want one real bad, then give us your address and we'll send you one. But anyway, so here's Icefin and here's Icefin. This is an early version. Anyone know where this is? So this is Antarctica. So this is underneath the ice, the sea ice in Antarctica. You can tell it's sea ice because you can see through it a little bit, where you can see the light coming through. And so this is Icefin actually in 2017. I said I would point out some mistakes. There's things like we hadn't gotten very good at floating things, so we had added foam and added modules and removed sensors. But it's really fun to think about it because this is version 1 and here is version 5. So we've gotten better, as it turns out, as one hopefully does. Over time. First, I have a quick question for everyone as well. Who believes in aliens? Not that we've contacted them or they've contacted us, but the fact that there could be life in space or somewhere else, right? So our background actually is kind of that. We're kind of space on Earth people. So we study analogs, but I wanted to introduce you to the aliens, the craziest aliens that I've met, or that Icefin has met. And what these are, this is the bottom of Thwaites Glacier, and these are anemones. So this is a type of anemone only found in Antarctica, as far as we know, and they burrow into the ice instead of burrowing into the seafloor or into rocks. And so it's very, very similar to the things you've probably seen scuba diving, but instead is in fact what I think of as aliens living amongst us. So you can see one of the fun things about this is that this very clear ice isn't all that common, but we got to the place where these were living and then we could actually see them up inside of their burrows. These are pebbles and rocks that have been churned up into the ice as it's been dragging across Antarctica. We're not going to talk about Thwaites Glacier much, but this is the fastest changing glacier in Antarctica, and that's why we were there, but we also, as I mentioned, met some aliens. And so a lot of our work is funded by NASA, and it kind of starts, at least for me, with this guy. So this is the first person who taught us that we're not the center of the universe, right? So or really proved to us, using science, that we're not the center of the universe. So this is Galileo. And what you're seeing up there is the drawings that he did. So this is from his original notebooks, is up in the left corner. And down here is from his draft of his first paper. By the way, that paper's amazing. If you want to read it, I'm happy to send you a copy or link to it. But he describes that the moon is a planet for the first time, right? That it has mountains and craters and valleys. He describes the phases of Venus. He says there's clusters of really densely packed stars. And the reason he did it is because he made the first telescope. So he found a new way to look at the universe. And what that really is something you could do yourself. Take any pair of binoculars and only look through one eye. But that's what he did to really revolutionize the study of the universe and how we see ourselves in it. And so for me, this is really important. So that's Jupiter with these 4 little points of light, and that's the Galilean satellites. So these 4 points of light moved from night to night, and he watched for 3 straight months just to make sure he wasn't crazy, right? And wrote all of those observations down hour to hour to show that these were moving. And we didn't have another way to explain this. We had been fighting, it turns out, for 1,400 years about whether the Earth or the sun was the center of the universe. And this was proof that, basically, of gravity. We didn't know that at the time, but that was the case here. Of course, he got kicked out, got excommunicated, spent most of his life in his house and under house arrest. What is it, Epercy Mouvet, right? So he was amazing. And one of the reasons that I think that's also amazing and kind of some poetic justice is that the satellites that bear his name turn out to be really amazing places where we might also find out that we're not the only thing that's important in the universe. So this one up here, anybody know this one? Europa, right? So Europa is the innermost icy moon of Jupiter. It's about the size of the Earth's moon, and on the outside has somewhere between 5 and 30 kilometers of ice, under which is a global ocean. For reference, the thickest ice on Earth is 5 kilometers, right? So the thinnest part of Europa is probably at least thicker than all of the ice that we have here. Something else that's important in this picture is what you don't see. You can't see the ocean that's there. What else about this stands out to you compared to other planetary surfaces? Cracks, right? So it's telling you something's going on. What else is not there? Craters, right? It's missing craters, just like the Earth. So it turns out that the surface age of Europa is comparable to the surface age of the Earth, which means that its geologic reprocessing is comparable to the rates that the Earth is reprocessing its surface, which is crazy because it's the size of the moon, right? And our moon has the same kind of materials inside of it, right? But it's cooled off. So what's going on here? So basically, Europa has been kept alive by tides from Jupiter. And so down below that this is what we think is the inside of Europa. It's basically like a very thin, icy layer on the outside with its global ocean underneath. And in contact with a silicate interior, the reason that's important is that it's the only place like that, aside from the Earth, in the entire solar system, really, that's this big and this geologically active. So it's really, really special. This is the kind of place that we think about for the potential emergence of life beyond Earth. And so that's kind of where we enter the story, and why we build things like this in the first place, is as potential future missions. So let's see, in October of 2014, this is a video I took from my cell phone of us launching Europa Clipper, which is an orbiter heading out to Europa to potentially give us the kinds of data that we could use to pick out a good landing place to one day get in, and I hope, underneath the ice shell of Europa. And so this isn't where you start technology, right? This is not the first satellite that's gone to space. Hopefully, with any luck, we can use the things that we're doing here to get ready for future types of spacecraft. And so this group of people and others, we've all done types of studies to try to study what we think would be a good mission to a place like Europa. And whereas like on Mars, we're kind of driving around on the surface like a car, that makes sense for that environment. But for here, where we're interested in the ocean and the deep interior, we kind of have to get through the ice and know what to do when we get there. And so that's what this kind of concept study was, which is that we land and we melt in, right? We melt and drill in. When we send something maybe that looks a little bit like this through the ice shell to map the ice shell and the ocean. And so these missions might look something like this, right? Maybe it's 15 kilometers or it's 30 kilometers. You land, you use basically nuclear heat. So you use uranium. Anyway, radioactive decay heats up everything. You start, you can also have some drilling going on, go through the ice shell, and take science measurements as you go through, pulling water into the inside of it, taking samples of the ice, and then we hope getting profiles or getting to one day drive around in the ocean, right? So it sounds kind of crazy, but most of this is pretty doable, and we're all working on trying to make that more doable, right? We drove cars on Earth for 100 years before we drove one on Mars, so we're trying to accelerate the pace of this, so maybe we'll be around for a mission like this. But that's what NASA's interest is. So we are funded on this project. Both the science that we just did was funded in part by the Heising-Simons Foundation, which is really interested in climate science, which we'll talk about as well. But NASA's very interested in helping people build the first steps of technologies as well as the satellites that end up going. And so what Icefin and this project really represents is our attempt at kind of learning, teaching ourselves how to explore, teaching ourselves which tools we use, which ones are useful in environments like the ones we'll talk to you about. And it's all with this kind of like long-term plan of maybe one day doing this on a place like Europa or Enceladus. So that's what funds our work, and so that's how this project gets to go to Greenland. So we're kind of playing with Europa in our backyard, right, to try to understand our own planet. And we've been doing this kind of work for, as I mentioned, since about 2014. So we've now worked, this is in Antarctica, so we've worked in McMurdo Ice Shelf and the Ross Ice Shelf. So the Ross Ice Shelf here in Antarctica is the size of France, right? It's the largest piece of floating ice in the world. It's amazing, it's very planetary in scale. So we've been there. We've also worked in Thwaites, that's that video that I was showing you as part of the data that we took underneath Thwaites Glacier. And then we've worked with the Norwegians and the British as well, up in, on the other side at Fimbolisen, or the Fimble Ice Shelf. And that, so we've got all kinds of different environments there. And so our day job kind of looks like this, actually, going underneath huge amounts of ice and mapping it all out. And so most recently, this project, we started working in Greenland. And so last year was our first trip. And so we left in February and headed up to Pituffik, which is the US Space Force base that's also cooperative with Canada, with Denmark, and with Greenland. I mentioned cooperative because that's really important. And so we had a chance to work up there, which is really great because it's also really cold and a really dangerous place to be. So we're up here getting to study this environment. And I mentioned that we're also, we may be funded to do future space, but we're really also concerned about taking care of our planet. So I wanted to show the fact that, people think climate change is new, and geoengineering or engineering of our environment in response to that is new, but it's really not. And so this is a photograph of historical seawalls in London that have been changed over time in response to flooding events. At the time, they didn't know why these floods were getting worse. We now know what that is, right? It's climate change. And at this point in time, right around this period, 1879, so the Arctic lost almost all of its ice shelves within the last 100 years. So the Arctic is completely different from when it was first being explored and when people were first living up there. But this is actually London's response to that without knowing that that's what they were responding to. So we know we've been affected by climate and we've been changing our behaviors based on that for a long time. This is a very, very noisy slide, but what this is showing you is projections of sea level rise. So basically how the ice loss that's happening in Antarctica and in Greenland, which is the largest unknown in the entire climate system, huge, what happens if we don't know exactly what's happening there? And so what you can see here is this blue, this dark blue is Antarctica, this light blue is Greenland. These are glaciers, so like mid-latitude glaciers, ocean thermal expansion, and water stored on land. And basically, as we change over time, the uncertainties in what these, in how big these are, starts to grow. You'll notice that the direction doesn't change, right? We know which direction this is headed. It's not uncertain because we think it might go up or go down. It's all headed in the same direction. The question just is, what do we do? And we're the unknown here, right? How do our future behaviors and our current behaviors affect this? And one of the things that makes this really, really hard to know is that we have almost no data underneath the ice where this melting is starting. And so that's what we're trying to do. And so the story for the technology side is one day I hope we go looking for life on Europa. But the story for humanity and for what we do is this story, right? How much are our coastlines going to be affected? It's not just a problem for people in island countries. They're getting the brunt of it right now, and they didn't do this, so it's worse. But we're all going to be impacted by this, whether we live there or not, because our economies are impacted by it, right? Our friends are impacted by it. Our loved ones are impacted by it. So that's why this is all really matters. So that's the bummer, and now for the fun stuff. So this is Icefin, this is the whole team that you've just mentioned, and so this is kind of why we're really motivated to study this system in Greenland. And because you're here at the Explorers Club, I'd like to also point out, so there's Paul, there's me, here's the whole crew, and Henry will be in this version of the picture this year, and so will Brandy. And so then we've got, in the background here, Rasmussen Glacier. So as you walked in, there's a sign-in desk. So you signed in over here for the talk. Right by where the coat check is, there's a desk right there, and there's a head. And that bust there is Rasmussen. And so this glacier is named after that person who was one of the first, at least Western explorers to be up in this region, trying to understand what was going on here. And so this is, all of the data that we're going to show you is coming from this dive, which is a really exciting one for us. This is what it's like to live in Rasmussen and Freukken's kind of front yard, I guess. So this is where Pituffik Space Force Base is. It's just transcendently beautiful during this particular time of the year. And this is actually that establishment. So these homes were built in the early 1900s. And then this is the frozen surface of the sea ice, of the ocean, that we actually get to take out every day. And so this is actually why we go when we go. We go when it's the coldest, or not the coldest, but very, very cold, in order to be able to drive along the sea ice, which makes our operations possible. And we chose this environment both because it has good access, which is surprisingly challenging in northern Greenland. Well, maybe not that surprising. But Peter Washam, a member of our team, who's not able to be here today, but hopefully is watching online, Peter started studying this system as a graduate student in 2017. So we also had a baseline of some data to compare to. So in 2017, they took the first data in this environment, or at least this first kind of data, or first data of this kind in that environment. And so this is pictures of Peter in 2017, and then in 2025, working up there. So this is a really cool environment because it's home to 3 different glaciers. And each of these glaciers, Rasmussen, Chamberlain, and Moltke, all have multiple just underwater rivers, basically. They're called subglacial channels that are bringing water that comes from a number of sources on the Kanuk ice cap and on the Greenland ice cap out to the front of the glacier system. And so either surface melt or subglacial water formed from melting or subglacial water upstream gets kind of discharged through the glacier system and comes out the front where the ocean is. And so in this environment, this fresh water actually then churns up the ocean water, and it mixes the warmer ocean water towards the glacier and can actually accelerate ice loss that way. So the fresh water is already melt itself at some level, either from climate or from pressure or geothermal, as well as it's also continually causing additional discharge. It can affect icebergs, it can produce them. And so we're looking in this really crazy environment here. And so here's Chamberlain, Rasmussen, and Moltke. So there's 2 channels in this one. I think there's 2 here as well, one really big one, and then 2 or 3 here. And these are pictures, so this is in the winter. And then during the summer, you can actually see this kind of muddy water here that's kind of drawn, this little outline is drawn here, that's discharging water from the whole system. So this is why we pick this environment, because we can study this process, we can get really close to these glaciers during the winter, and we can stay a safe way away, and then we can send the robot to do the work up really, really close. And so we're going to get a chance then to go to this environment and find these, what we're referring to as these warm lines, right? These warm subglacial water channels, the pathway of warm water in towards the glacier itself. And so we're trying to map these processes to see how they physically operate. We know they're happening, but we can't measure it directly. And so that's why we take things like this to Greenland, and why they're so useful. And so that's what we're going to kind of tell the story of here. Why is it happening? Well, we know. Actually, some undergrads and Peter in our lab have been working on looking at long-term data. And so what it actually shows is that in the environment there's been about a 2.5 degrees C warming in the last 73 years. And there's been a general trend upward and a lot of increase in the number of degree days above freezing, basically. So we're not only seeing warming, but we're also saying number of days above freezing is going upwards, which is what we would expect given what we're seeing everywhere else. So we know it's warming, but we can also look at the remote sensing data and see that the glaciers have been moving backwards. And so these glaciers have been rapidly changing. And so just over the last 30 years, which is when we have really good satellite data, Moltke has retreated 6 kilometers. Rasmussen has retreated 1.5, and Chamberlain's retreated about 2. In fact, Chamberlain now is almost not in the ocean anymore. It is transitioning to being fully on land, which is something we haven't really ever measured very well. And so this is going to be an interesting one to watch. So this one is coming off the Greenland ice cap, and these are coming off this smaller ice cap called the Cannock ice cap. So we know it's changing, so we needed to go up there. More importantly, I mentioned that Peter had data from 2017. So this is a temperature profile, and what they did is they took an instrument called a CTD, a conductivity, temperature, and depth instrument. So you're getting the salinity of the water and the temperature, right? So for example, if you have melted glacier water, it'll be less salty than the rest of the ocean, right? So that's one way to think about it, and you get the temperature signal there too. So this is the temperature in 2017, and this is the temperature in 2025. So the surface temperature is fine up here, but most of the time in Antarctica, we're talking about parts of a degree of warming to the ocean, but this is 2 degrees in less than 10 years, which is just crazy. We didn't know that. We knew that it was probably going to have warmed up, but none of us thought it was going to be 2 degrees, and so that's absurd. So it turns out there's another big warm line coming at us, right, and it's this warming ocean water from the Baffin Bay that's coming into the system. So it's a cool place to go looking. And at this point in time, we're going to introduce you to the robot and what we did with it. So.
Oops. How's it going? Which button is it?
It's the big green one that has an arrow.
No, but the laser.
Oh, it's the one that looks like a
The
laser.
laser. There we go. Sorry. Hey, how's it going? As I mentioned before, my name's Matt Meister, Brittany's lead engineer. I've worked with Britney for longer than I can count on 2 hands. Is where I put it. And I started as a student way back when in Georgia Tech, so I've got to see a lot of this from the very beginning. And so one of the things that was interesting about Icefin at the start, and kind of Brittany's constraints with it, is I have to be able to take it on an airplane, and I have to be able to fit it through a borehole that we can drill with an ice auger. Which, if you look at other vehicles that exist for polar science and even off of ships, they don't quite fit the bill. They're roughly the size of this table put together with a couple more feet, and need cranes and teams of 20 or 30 people, and are really, really expensive. And so a long, long time ago, we kind of sketched out this idea of Icefin. And as Brittany mentioned, this is another photo from, I think this is a 2018 or 2019 season. It's a little bit different, but kind of the important things to note about it, other than its size and shape for transport, is where we've put different instruments and why. And so you can kind of see, and we'll walk through it, we have some science sensors and cameras up front, we have some more science in here, and then there's some thrusters and a few other instruments that I'll walk through in a little bit closer. But all of these kind of play an important role of where they're placed and why they're placed where they are. So this is Icefin in 3D space, if you will. You get a quick little tour of where everything is that you can't see kind of up front. But nope. There we go. So up in the front, you can see we have, I'll call it our clean water science sensors. So these are where we want the very first measurements taken with the least amount of disturbed water from Icefin. Because what's really important to know is once Icefin touches the water, everything along the back from a conductivity, temperature, biology gets disturbed, and we don't want to interfere with any of it in the back. So we have a CTD, as Brittany mentioned, up front in the red. We have some cameras on top and bottom. We have a dissolved oxygen sensor measuring the oxygen in the water, and then we have a forward-looking sonar. So I don't know if any of you saw out front, but you'll see in a little bit, it can do a 2D scan of what's in front of us. And then right behind that, we have thruster modules. So we have one in the front and then also one in the back. We can control 5 degrees of freedom with Icefin, everything except roll. And we do that with putting heavy instruments on the bottom and more foam on top. Underneath, and the next module, I'll call it our modular science payload. And so this is really what makes Icefin unique compared to some other vehicles. We can actually swap that out, and we'll walk through all of the instruments that we can place there. But that's really where it's project and science question dependent on what we fly. Then you'll see the electronics. We have a picture up here of what it looks like. But all of our power, processing, communication, muxing, anything that Icefin does, we do it on board, and then we send it all back to the surface through a single fiber optic cable that's Kevlar jacketed, and that's what we actually use to raise and lower the vehicle through the borehole. Then behind that, we have our navigation module. So we have a couple sensors. We have a depth sensor. We actually have 2 of these now, DVLs, Doppler acoustic velocity loggers. So if you think of like an ambulance as it's driving, you hear the siren changing, it's doing that along the seafloor. So we get vehicle speed on the seafloor and on the ice bed. We have HD cameras, lights, and in the back on Icefin, we actually have a USPO this year to kind of help narrow in on some of our positioning data. And then another set of thrusters in the back, like I mentioned, to control that hovering capability, and then a main thruster in the rear, and no vehicle is complete without a set of backup cameras. So that's kind of Icefin in a nutshell. And what's cool about it is, one, we can take it wherever we need to go. But what makes it unique compared to a lot of other vehicles is this science payload. And so right now you can see we have a multi-beam sonar. So essentially what you're seeing up front, but in a 3D space of the topography of the seafloor or the ice up above, depending on which way we rotate it. But we can change this out for a microscope or a water sampler or higher definition cameras or a mass spec or science blank is what we can put in here. And so that's what makes Icefin cool, is we've built this platform that not only does basic functionality of these larger vehicles, it gets you to a spot, it takes basic science data, but it gets you that second level of data that not a lot of these smaller vehicles can do because we've built this modularity in. And so what we'll do with Icefin, and you'll see it more in some of the data and kind of how we launch and recover, but it's how we utilize being able to swap this payload out to go back and study the same thing, not just over and over with the same instruments, but having the capability to swap that out. And so there's lots of videos and everything of where Icefin's been. I think even this is probably even higher now, but a couple hundred hours. We're over 100 missions at this point in both poles, hundreds and hundreds of meters of ice, and seen grounding zones in Antarctica, the ice shelves. And so really, it's the only vehicle of its kind that's capable of getting to these really hard to study areas that we can either do through the sea ice using ice augers or hot water drilling through boreholes on the ice shelves. And with that, I will hand off the electricity to our electrical engineer.
Hey everyone, as Brittany mentioned, I'm Daniel, I'm the electronics engineer. And as Matt so lovingly presented, it's a big robot, pretty complicated, and a lot of stuff going on. Most of my job is just this little section right here. There's enough going on in there to keep me pretty busy. I won't go over all of it right now. If you want to talk like nitty-gritty with me later, that's fine. I find that talking about electronics can like rival some strong sedatives in terms of putting people to sleep. So yeah, I'll keep it brief. As Matt mentioned, kind of everything that we do with Icefin is done on board, and then we relay it up to the surface, and all of that is really handled right here. This kind of shows what it looks like in the ideal world. That shows what it looks like in the real world. It's a whole lot more messy, and more of my job than I'd care to admit is like figuring out how to fit wires into certain places. But basically what we have here is this big aluminum cube is our computer. And so that handles all of the subsea processing. When we send a command to Icefin, it's parsed by that, and then that tells Icefin what to do. Down at the bottom here are all of the batteries. We use 20 basically laptop-sized lithium-ion batteries. That gives us about a 6-hour mission time right now, and we're trying to improve on that all the time. We set numerous endurance records in Greenland, both in distance and time, which was really cool to see. And we can power, in the newer generations of vehicles, up to 32 different subsystems using these electronics on the top, just a bunch of switches. and 3 different groups of thrusters, and we have a whole suite of standard communications for off-the-shelf sensors, custom sensors, which makes it really easy to kind of develop to that modularity. As Matt mentioned, we're able to communicate with all sorts of instruments or designed to kind of well-known specifications. And then at the top there is kind of the heart of the communications, and that's what turns the electrical signals into fiber optic, which we can then relay up to Icefin over up to now 5 kilometers of tether, which gives us a great driving range, and it's a very reliable communications link, which is fantastic. And I think that's kind of that's me. I'll hand it off to, I don't know who this is, Henry.
Hello, my name is Henry. I am a very recent grad. I will make this quick because this is my one slide and I have about like 2 minutes in the limelight. So one of the things that Britney mentioned that our lab does is we do research and we do development for platforms for planetary exploration, and believe it or not, Icefin is not the only technology that we are developing for planetary exploration. And one of the parts of the work that we're doing for this campaign that we have going on right now, Show Up is a NASA P-STAR program. One of the things that we're spending your tax dollars on is developing more platforms for doing this kind of science. So one of the things that I spent the past semester working on is this base station over here. This thing is called Barnacle. It is the best acronym I've ever come up with. It stands for Below Arctic Robot for Navigating, Autonomy, and Charging for Long-Term Exploration. It is a docking and charging station for Icefin. So the idea is that we hopefully will someday be able to drive Icefin into a docking bay down here. There's a linear actuator that will press down a wireless charging pad onto the robot, and it will meet a receiver on Icefin, and it will allow us to recharge Icefin without having to pull it up through the ice, which is great because that's very difficult and dangerous, and no one wants to do it if we don't have to. And another one of the instruments that we're working on is SWIMS, which Jorge is going to talk about in a second. This thing is an underwater mass spectrometer. And we're also looking into new tools and methods for doing data processing, including using machine learning to analyze the data that we collect, because we collect a lot of data, huge volumes of data with this robot all the time, and doing all kinds of cool new mapping stuff with our forward and downward looking sonars. So that's it. Thank you.
Yeah, and so I'm Jorge. I've been working on, as a part of my PhD project, on this immersible under ice mass spectrometer. We do love our acronyms. And it's called, it's written SWIMS, and as a Spanish speaker, I always pronounced it in my head in the Spanish way, and it took me like a few months to realize it's like swims, like swimming. So essentially, the submersible under ice mass spectrometer is a new instrument we're building that we eventually plan to put on the modular science bay of Icefin as a way to be able to probe and look at the dissolved gas concentrations in water beneath glaciers. So this is the first generation, and it went to the first time to the field in Greenland last year. And it was just a test to see if we put it in the water and it turned on and it didn't drown and everything was working okay. And so we are working on a newer version that's going to also go with us in the field in about a month. It's been a lot more complex in the way we can operate it, with a few more different instruments that we can also measure pH and dissolved oxygen. That's different from the one in the mass spectrometer, just doing it optically. And it'll be able, more importantly, to be deployed at deeper places, which will help us to put the instrument in where we think that outstream of the subglacial channel is coming from. And this is important because with the CTD, Britney sort of teased how we can do different types of water masses, or water that comes from different origins because it has a different density or salinity imprint. But ahead of that, we can also look at which they mentioned the water that's coming from the subglacial channel can come from either surface melt that's entrained, or it can come from some basal melt that's coming from pressure or hydrothermal channels. And those have very specific imprints of dissolved noble gases that we can use to tell where that water is coming from. We can quantify what's producing all that water that's coming from the subglacial channel. And apart from that, we can also look at some, let's say, biomarkers or imprints of biological activity. And the most important part is we can also sort of tease out a lot more of the carbon cycle, and we can look at some of where the carbon is being dissolved in the water. And this is me deploying it for the first time. So for this first field season, we just had a 5-meter cable, so it was literally just a literal just dip in the water. But we've had some of the other Icefin electronics and architecture for it to be able to be deployable with a fiber optic cable. So the 5 kilometers of tether we have for Icefin, we can also use for this, although this doesn't move, so it's just gonna go up and down the couple 100 meters of depth of the water inside the fjord. And I really like this picture because you can see the whole Icefin operation and the number of people it took. And I was just kind of always sitting outside with like my little laptop, just observing my instrument and making sure nothing was going wrong. But we're really excited about the science we're gonna be able to do with the instrument this next field season.
Hooray! Okay, so how do we get the science done? Matt mentioned not just the modularity is great, but we've also gotten better at this part. We personally have broken the robot in half before. We don't do that anymore because of the way we do our launching now. So in this operation in Greenland, we're driving across sea ice, and so that's about 1 meter thick of ice, right? Which doesn't feel that comfortable probably to most people. I'd like a little bit more than 1 meter, but it's actually, you only probably need about 6 or 7 inches, and if you've got a snowmobile, maybe it's 8. Still, no one feels that comfortable driving on 8 inches of ice. So anyway, although I guess maybe some of you did that today to get here. So. But this is what it looks like when there's ocean underneath it. And so we'll actually take one of these ice augers. I don't know if we have a picture of one in here, but basically the same thing you would use to go ice fishing. So those are the biggest ones that you can commercially get are 10 inches. We are a little bit fatter than that. So we have a special blade extension that can actually make this about 12 to 14 inches. And so this hole through the ice goes down all the way through the ice. In Antarctica, we've gone through 5 meters of ice. That's a lot more drilling, it turns out. But then we drill this hole in the ice, and then we lift the vehicle vertically. Let's see, we've got Matt, we've got Paul, we've got Daniel, Jorge, Francis, lifting the robot. And so we lift the robot vertically, and then we launch it down using the tether. So you can see that tether here. This was 4 kilometers. Now we have a 5 kilometer tether, so we're excited to hit the end of that one, hopefully. And then we'll kind of take the robot down. And we've gone through up to about 750 meters of ice with this, 600 meters at Thwaites, for example. This is what it looks like. So this is a day in Antarctica when we got a time lapse a few years ago. So we're a little bit different robot, but still pretty good. So we would drive out. It might take 2 hours to drive out there, build the robot on site. Actually, this is Francis's first field season too. Lift the robot, put it down to go do its job. Beautiful view of Erebus Glacier there in the background. And now I'm going to turn it over to Francis to talk about ops.
Awesome. All right. So this is what it looks like inside the tent. We just saw that outside when we're conducting a dive. So we'll have a couple of people front and center in the tent, and then a bunch more observing behind. What you're looking at here is our topside setup. It's what I've tried to recreate out there in the other room. I think I'll also have a video walking you a little bit through it. But essentially, we set up all of this in the big yellow tent that you saw. We have computers and screens and a PlayStation controller to drive the robot. It has a lot of autonomous capabilities. We can send it to go do a pattern, but we find a lot of use in actually driving the robot by hand to get into these really difficult environments to investigate. Let's see, that's the next one. All right, so I think it will just play automatically. Or I have to press a button. So this is what we are looking at, or part of what we're looking at when we're driving the robot. This is a software that is by Green Sea Systems, but a lot of the individual systems in order to read our sensors are actually coded by us. And so there's a lot of kind of Band-Aid solutions, maybe a little bit nicer than Band-Aid solutions, put on top of this commercial software. You can see now a zoomed in map with a view of the robot. The robot has all these sensors that Matt was talking about to help us figure out where we are. We can kind of, by telling how fast we're going and for how long we're going that speed, we can back solve, integrate, and say, this is how far we've gone, and Icefin will tell us where we are. We have all of this is signals coming back from the robot. That's why we get hundreds of gigabytes back from mission, because we have a lot of information to process at any one time. And scrolling along the side of the dive to go see this, I'm actually going to go back and forward. We control all of the robot with buttons. We can turn on and off our sensors. That sends a signal down the fiber optic tether to the robot. And we can get all of this information back, read out. We're looking at minute changes in temperature to tell us where we are, how hot the water is at minus 0.6 C. That's not actually that hot, at least to me. The salinity, turbidity, how cloudy the water is, all of this data helps inform where we are in the channel, or where we are in the fjord, and are we actually in that subglacial channel. So I'll go to the next screen. This is the other screen that we're looking at in the tent, and this is our cameras and sonar. And so this is what the robot is, for lack of a better word, seeing. So this is us with our top and bottom camera. Unfortunately, I was not able to get the other two, the backup one and the up-down one, as we're literally running into a glacier. That seems like it was a mistake. It was not. As Matt was saying, we like to get our undisturbed water right up on the nose to get all of those sensors in it. So this is actually a very fine-tuned operation to get all of the data right on the iceberg. Right. What you see over here to your right is our sonar data. And so all of the bright reflections here are surfaces reflecting back. So there's something 20 meters right in front of us that is probably a wall, an iceberg, or something like that. And so that is what we're looking at inside the tent, telling us where we are. And likewise, this is what the surface of the ground looks like below us. So it's a little bit slopey in this particular area. All right. Oh, and is this also a video? Okay. Oh, this is a video of the robot actually driving. Is this from our little robot? Mm-hmm. Sometimes we'll take down a smaller robot just to get really good sort of video of what Icefin looks like underneath the water to prove that we actually do all of this underneath the water. This is right beneath the ice surface, so that's what the white thing is in the corner. Cool.
Awesome. Thanks. So this is also a really great science transition. Oh, I think actually we'll go to Veronica pretty quick here, because the reason that this video looks so murky is actually it's particulates coming out from underneath the glacier. So in Antarctica, this is not what it would look like. It'd be just clear, just beautiful clear water. But here where we have these active outflow channels, that is all particulate that's come and been disturbed and is flowing out through, and that's why it's all kind of murky in the background there. So what we did over the course of 7 weeks spring, so February through April of last year, and footnote, we're about to go do this again, was to drive and do a couple of different missions. So first we did that data that we showed where you could see that that it had gotten so warm, that was taken across here. So we put together 3 different dives. In fact, this is one of those distance records that we had. It was like a 6 kilometers worth of tracks and operated just a little further than we probably should have with the battery. But we got these really, really great transects. And so we actually, if you saw that picture, we actually dive the robot up and down, and you'll see more examples of that so that we can map the whole water column as we're going through. So we're not just going straight forward this is a hydrographic survey where the mode that we're using is let's map the water column, and that's our focus. There are other ones like let's map the channel. So mapping channel, you're going as flat as possible into the channel itself. So we did 3 dives to get that context data to go and compare to the 2017 data. And then both Peter and Veronica went back and actually added even more data with CTDs. We did 1 dive at Chamberlain. We did 4 dives at Rasmussen, including 3 dives into the subglacial channels. So we actually mapped this one twice and then this one once. And then we did 2 dives over at Moltke. Unfortunately, we got really bummer luck where the ice melange out in front of the glacier was like 3 or 4 kilometers from the front of the glacier to where we could be safely positioned. So we weren't able to actually get under Moltke this particular season. So we're still going to try to do that this season, but you just have to get lucky because this one's really, really active. This is the one that moved back 6 kilometers, right? So it's losing ice really, really rapidly. And then we also did 2 dives over here. We actually mapped the area and the bathymetry near the station, near the dock that they bring ships in because they don't have bathymetric data because there's ice there. And so they needed it for that to check for depths and hazards and things like that. So we actually did some like service work for the station, which was really cool because we actually got to have folks from the station who had been up there come out, and they walked out onto the ice and came and visited us for the day, which was really lovely. So then we got to do a whole bunch of gathering data in these subglacial channels. And here's at Rasmussen, which is the one that we're going to talk to. So, Veronica? One more? Oh, I guess I have one more. Okay, yeah. So, one more slide. So basically what we're talking about is those worm lines, right? So this is the face of Rasmussen Glacier. And please raise your hand if you can obviously tell where the subglacial channel in that is. So this is a 4-kilometer wide calving face of this glacier. And what we're looking for is 2 30-meter holes at the bottom of this. So it's about 250 meters of ice, 200 meters of ice. So we're 200 meters in this direction, it's there. I'm smart. And then it's 4 kilometers in this direction. So we're looking for the 30-meter hole in the bottom of that. And so that's what we were going to do. And so those plumes, the turbidity, the oxygen, the salinity, all of that tells us what's going on. So if you use the salinity, the temperature, and the oxygen content of the water, it's kind of like a fingerprint for the water column. It tells you where that ocean water was formed and what it's interacted with, right? So the oxygen could come from interacting with the atmosphere or with melting glacier ice, right, which contains more oxygen in a little bit different amount. The salinity would also tell you part of that story, right? It's fresher when you've interacted, and fresher and colder if you've melted ice into the water. And so we can put all of those things together in addition to the sonars and all of this other context to actually tell what's going on and to find these subglacial plumes that we really don't understand, map them, follow them back, and go looking for this. It turns out you can also see it a little bit. When you melt the bottom of the ice, it'll actually draw the surface down a little bit. So our guess was that it was right over here, and it turned out to be pretty much there. But that's the kind of thing that's kind of a little bit of a challenge and a little bit of exploration in the science that we're doing. All right, Veronica.
Hi, I'm Veronica. I'm a PhD student in oceanography, and basically my role is that after a dive is over, they set me loose on the data, and then I get to pull a story out of it and make figures and do analysis. So here are the 3 dive tracks from the channel dives that we did, and so there were 2 here from our site that we call R1, and then 1 here at R2. And then I'll show some of the data from actually inside of the R1 channel. And then here is some sonar imagery. So it's an example of the kind of thing that we see from Icefin's forward-looking sonar. So as was previously said, everything that's a bright color is ice or the seafloor reflecting back at us. This is partially the entrance to one of the channels. I think it could be a video. Yes. And so what we see is that there are these bright reflectors on the sidewalls, and that tells us that basically we are staring straight ahead into a hole in the ice, and then we have ice at our sides because, again, we are inside of this channel. And I'll have a better image of that on the next slide, but you can picture these channels as being kind of like a subway tunnel, and so there's like an arched entrance and then walls on the side. Okay, so here is a 2D cross section of what we actually see inside of the channel. So the white is ice, blue is the ocean, and then brown is the seafloor. And then everywhere the Icefin dove is colored according to salinity. So that's this track right here. And I have Icefin right here that is not to scale. So one of the things that I want to point out is that the salinity is around 33.1. Does anyone know what typical ocean salinity is like on Earth? Yeah, exactly. So 33 is pretty standard for the area that we were in, but basically what this tells us is that there is ocean water inside of the channel. This is pretty important because oftentimes when modeling ice loss from glaciers, the models assume that after the glacier is on land at that point, that there is no more melt occurring because the ice is in contact with the ground. But what we see here is that there's actually ocean water inside of this channel and underneath the glacier. And then if you recall from the figure from earlier, the water deep in the ocean was actually quite warm. And so since we see high salinity here, that tells us that there's also warm water inside of the channel as well. And without getting too far into the physics of ocean water mixing, basically, if you see fresher water that typically corresponds to direct melt from the glaciers, and that's also very cold. And so if you have seawater coming in, that's warmer, and that can drive melting. So from this spot right here, that is the sonar image that we see. And so you see this nice arch shape, and that's telling us that we are about to enter into the more main part of the subglacial channel. And then here is around 10 meters tall and 6 meters wide. And then here's our second entry to that same channel. Same deal, ice, ocean, seafloor. And then what we also see is that the salinity decreases quite a bit at the ceiling, so right by the ice. And that tells us that there is melt water there, both from direct melting of the glacier itself and also from subglacial outflow coming from upstream of where we are. And then there is that sonar imagery. So again, we have these sidewalls here, and that tells us, again, that we are driving along the channel. Here it was 9 meters tall and 8 meters wide. And then at the other channel, that one was much bigger. And so here it's around 32 meters tall and 16 meters wide. So a much larger cavity and also much more uniform. And again, you can see that there are these two sidewalls here. So then, I'm gonna skip that. Okay, so here's a 3D map of our dive track in front of Rasmussen on this dive. And it's colored according to temperature. I think it's a video, yes. So here we see that the deeper water is quite a bit warmer, and then it's much colder towards the surface. This is partially because that colder water is a lot fresher, and so it is more buoyant, and so it will rise to the surface, but also because the air is very, very cold, and so that can also directly cool the water. And then finally, this is how we can identify subglacial outflow plumes in front of the glacier. And so when water is coming from upstream, like on the actual ice cap, that will flow out through these subglacial channels, and we can identify that because that water is going to be very turbid, or basically very dirty, and that's because as that water has been flowing along the bed of the glacier, it is picking up dirts and other sediments, and so that gives it a very high turbidity, is what we call it, and it's seen in this strip right here, so that's around 25 to 35 meters deep, and that tells us that there is a subglacial outflow plume there. And then finally, here's a 2D cross-section of that area in front of the fjord. So we have Icefin's dive track going up and down right here. And then again, this time it's colored, yes, it is turbidity again. And so again, here's that strip of more turbid water. And that, again, tells us that there is a channel here where that water is coming out from. And that's also what helped us identify the channel's location.
So I wanted to just quickly go back here, just so you can see from, so this is what a raw data product looks like. So like Veronica wasn't kidding that we basically come back, so these are very, very long days. We'll probably spend 12 hours or more out there, and it's minus 35, so it's really comfortable. But that's why we have jackets. Thank you, Canada Goose. But what we can do is we can pull things like this off the robot pretty quickly. So this isn't really processed. So it's showing actually everything that's being measured by the vehicle. So this sonar would be pointed down here to measure this. So I'll show you some of that in a minute. These are the sensors Matt mentioned that can ping off of the surface of the ice or the seafloor. And so this track here is coming from that sensor, the DVL or ADCP, is tracking the ice and measuring the ice. And you can see this, we're under sea ice, little chunks of thicker sea ice, bergy bits, little pieces of icebergs. And then here we're actually underneath the calving part of the glacier. So these are all icebergs out in front of the glacier, and now we're under the glacier itself. So you can see all of that here, and the seafloor is measured by the ADCP that's pointing down, and then the detailed three-dimensional map is the one I'll show you here in a moment. So everything on here is measured from the robot during those dives. And so that's what this spectacular figure that Veronica's put together really shows that very well, right? That in this water, right, this is the dive track she mentioned. We've got all of these different signals coming in, the ones that Francis was mentioning earlier. But we also have things that are works in progress. And in fact, we have a new way to process this data, but we haven't even had time really to use that. So what this is now the shape of the seafloor inside that channel. So we kind of drive in and we kind of turn this corner here. And this is old grounding line positions, basically the edge of where that glacier was. Probably this motion of the glacier also will cause the water to change paths. So we're going to be figuring out what the signatures of all of this melt are, and this sedimentation that's also driven, right? It's just like a delta. So this is the bottom part. So think of this like the delta that's coming out underneath the glacier. So we're still working on this sonar data from underneath it. Some other data that we took, this is us not successfully being able to get around an iceberg that had collapsed in front of the Chamberlain channel, which is why we don't have any Chamberlain data. But this is how you try to kill your robot. So this is the view. Oops, sorry about that. We'll go back and go forward. So top, bottom, this is on the front of the robot, and this is looking down. So we're actually in kind of a tube of ice because there's an iceberg that had kind of collapsed and was blocking our entrance, but we could see and sense all of the water flow coming out of there, which is why we were trying so hard to find a pathway in there. So the robot physically can't fit between it anymore, and that's when we consider too far. Is when we can't fit. So with the channels, we went all the way back, right? They started at 30 meters. We went all the way back till it was 2 meters, and then we got a little sketched out, right? So under Thwaites, we put this robot into a water column at the grounding line that was basically twice the robot. So it's a challenge to operate in those environments, but it's still pretty cool. And this is an amazing picture. This is looking up this time. And this is the bottom of sea ice. Oops. This is the bottom of sea ice, which is the blue stuff. And the green and the red are icebergs. Then they're the bottom. So this is actually upward-facing sonar of this ice matrix that's kind of trapped in here that Francis processed for us. So you can see all the little icebergs. This is also really important for figuring out how the ice is falling apart, how big those pieces are, how this material works. So it's fascinating as well as important for climate. So we're still working on how to do all of this. And that's a process of everybody working together. So this was amazing. We did 10 science missions across those 7 weeks. And then we had 12 science missions and then two science dives. Or 2 mapping dives. We had, multiple new instruments. So Henry said, one day we're going to catch Icefin with it. Well, actually, Francis drove the robot into there and caught it. It was pretty cool. We got to get our technology out. We got to make these important climate measurements that we're continuing to work on. We went into these 2 subglacial channels, and we were mapping these changes and trying to really contribute to understanding what's happening there. One of the cool things that we're going to be doing, right, is we're heading out on February 18th. So last week we shipped our last shipment of stuff up to Pituffik. Or down to McGuire to go up to Greenland. And so we're planning for this again. So it's going to be the evolution of the project. One of the cool things that we're going to get to do this season is to not only sample in the water column, so we'll drill a hole and we'll actually take water samples as well to get even more detailed analysis than we can do on board the vehicle. But we'll also, for the first time, do dives where we replace the sonar module with a water sampler that we can hopefully take water samples in those channels. So we can actually get direct measurements of that environment for the first time, which would be, that's our reach goal for the season, and we're really excited about it. And I wanted to give Brandy, who's the newest member of our science team, a chance to talk about some of the analyses that we're going to do. So in addition to microbial, so who's living there, what do they do, what kind of organisms are there, right? The backbone of productivity in the region, right? Affects fisheries, all kinds of things. But we've got some other plans for that water sample as well.
Hi, Brandy, newest member of the science teams. My background is in isotope geochemistry, climatology, and so I'm really stoked about the samples that the team has worked so hard that we're going to be able to take this year. And that's sort of the story of biogeochemistry that happens here. So most of us believed in school that biology was a separate subject from physics, was a separate subject from chemistry, and actually that's not the case. They're all sort of intertwined, and thus is born the field of biogeochemistry. So what this season we're going to be able to do is actually look at how the physics is informing the chemistry, which then informs the biology. So one of the things that's unique about the polar regions, which make up about 20% of our planet, is that we don't have rivers. We don't have mass flowings of liquid water eroding the surface of the planet and delivering nutrients to the water. And so one of the ways that polar regions have gotten around that are through subglacial plumes, right? So the physics of this brings the water out to the sea, and it can interact with the biology that's there. This is also an analog for planetary processes, right? Like we talked about in the beginning, the lack of craters means that there's overturn, right? Things are mixing. And so again, that's that biogeochemistry that happens on our planet and perhaps on others. And so that's something that we're going to be going into this year. And I'm really excited, and it's only because of all the work that these guys have done in the past.
So we're really excited about it. And to kind of wrap us up, we'll bring our large mammal specialist up here to walk us through an important verse here. But here's the team with our flag. So we were a flagged expedition last year. We also took the Submariner that's down there in the display case with us as well. So this is that day that we did our, this is actually the day that we did our second channel dive. Or the second channel. And then this is a picture not long before we left, and you can actually see there's a sled dogs here and a sled here. It was Greenland week, so the base is totally open, and so folks from the community were coming out to visit us. So it's a spectacular place, and we felt very fortunate. So, Paul.
I love that this is typical of my contributions to the team. I sing. To quickly add a context, that photo on the left is looking northwest at the Northwest Passage. That is called Surprise Bay, I think. Is it Surprise? Yeah. The HMS Investigator and Surprise. After Franklin disappeared, in one of the first searches for him, I think it was 1848, one of those ships got lodged in an ice floe and carried north to this bay, where it overwintered at this bay. That's the earliest Western contact there. And then that, as Britney mentioned, that the base itself essentially was established in 1903 by a member of the Explorers Club to be a base for science, a base for benevolent, it was aspired to be benevolent development of the indigenous communities that were there. And it was pretty special. So with that, here is, and one final very quick story. There was a day where it was a beautiful Sunday, and the base community played beer pong. It set up beer pong tables on the ice. And they brought out a car with very loud speakers that they brought from the Top of the World Club, the bar that is on base, and they set them up on the ice. And they were playing Pink Pony Pong and Pink Pony Club and songs like that. But at the end of it, they were kind enough to play this song, and we bumped it over the ice looking out northwest. So I'd like to invite you to join me. We'll just sing the last verse. Ah, for just one time, I would make a northwest passage to find the hand. Please join in. Glen reaching for the Hobart Sea, tracing one warm line through a land so wide and savage, and make a northwest passage to the sea. You did great.
All right, and charismatic megafauna while we take some questions.
All right, so if you'd like to ask a question, please raise your hand and we'll bring you the mic.
You may sing it if you wish.
Not everybody at once. And if nobody asks a question, we'll just have more songs.
Thank you. Brilliant presentation. Could you explain more about the collaborative part when you say that is very important?
Sure. So, for example, we're a science group, right? So the mission of the base actually up there, which we didn't really highlight at all. So this is actually this video down here. So this is a seal that came to find us when we were at Rasmussen. But this is actually a video off the pier, so where they're bringing the ships in. So that place is kind of special because it is a collaborative base that's all radar technologies. Then what they're doing on behalf of NATO is to watch for ballistic missiles, but also they're looking for also asteroids, tracking satellites. So there's a ton of work there. And so the Canadians have military that go up through there. They also land and resupply some of their locations in the Arctic via Pituffik. It is on Greenlandic land, and the base operations are also run by Greenlandic and Danish citizens. And so aside from the radar tracking and the planes landing, so the plane operations, the actual, flight control and all of that, aside from those elements, everything is actually run by Danish or Greenlandic companies and people. And so it is, and like I mentioned, and the Canadians are also involved, right? So it is an asset. And when you're up there, there's all kinds of flags of different nations there. But one of the things that they're also letting us do is be scientists working on these things, right, here on base. And then we were able to go and take tours, and they were able to come out and see the operations. We were able to help them, and they were able to help us, right? So we don't have to worry about polar bear fences. Paul and I carry rifles out into the field in order to hopefully not have too many interactions with charismatic megafauna, but they were there. They saw us. We did not see them. But that's what we have to do. And so that being there in that environment with that cold and that and those dangers, actually being able to work from a place like that is actually really helpful and makes this kind of data, which was also unique because of the time of year. Most data in Greenland is taken in the summer and it's taken in the south. So we have very little data from the north. We have very little data from anything close to the winter. So this is really important for that reason too. And so that collaboration is making the science possible, even though that's not the central mission, but they're allowing us to go up there. And we were putting the robot together and storing our materials in the same place that they're parking the fire trucks for the airfield. Right, so it's truly collaborative, and most of the people that are up there, right, they self-describe themselves as the 1%, we'll call it weirdest part of the Air Force, and it's really people that are science and space nerds that are trying to figure out space situational awareness. Most of what they do is communicate with satellites, track satellites, debris, things like that. So it's mutual benefit for everybody, and that really was what it was like when we were up there. And I'm not lying about that. It's also it's an interesting history, but it's I would say not in lockstep. No one up there, and our experience up there was not what I think you would see on the news right now. And I think it's really important that we treat it the way it's intended, which is as a collaborative space.
Our next question will come from Captain Davis here of the research vessel Robert Gray. Ask him about this really cool ship afterwards. And we'll have time for one additional question after this.
Thank you, and thank you for the Stan Rogers also. Very well done and a wonderful presentation. The numbers I was hearing as far as the fiber optic cables and the thickness of the ice seem to coincide, especially in Antarctica. If that's the case, I'm hoping I'm wrong, and that I will understand better how y'all maneuver when you get to the end of your fiber optic cable. Do you double down, and are you afraid of pulling the plug while you're under there, and what happens if you do, or is there another method that you deal with that?
Yeah, okay, so that's a great question. So what we have, our longest tether is 5 kilometers. The thickest ice that we've personally been through is 750 meters, and that was carved into a subglacial channel in Antarctica. So we're going through there, so it's only about, it's 600 to 700 meters to get through the ice. And then from there, so then we have 4 kilometers of range if we have the 5 kilometer tether, right, plus or minus. The robot, so we're getting longer and longer tethers because we're able to drive farther and farther. So for a long time we had, a 4 kilometer tether, but we could probably make it about 2 kilometers. And then we can make it 3 kilometers. And now we're making it 6 kilometers and we have a 5 kilometer tether. So that's kind of how we've done that. And so we plan our missions based on what the science goals are, and we try to locate ourselves in the best way possible. But we'd have any kind of, if it's a channel dive, what are we gonna do? If it's a hydrography dive, what are we gonna do? But in terms of emergency operations, we actually have done that a large number of times. So the tether is both the best thing because we can put the robot through the ice and bring it back, but it is also like the world's worst necklace, right? You leave a necklace alone by itself and you come back and it is in a horrible knot. And imagine that under the ice, because that's what it is. We call it dangerous spaghetti or something else. And it's terrifying. So it can tie itself, and it will tie itself around everything and anything. And so, for example, this last time we got it wedged pretty good in some of those bergy bits. So they're beautiful. It's what we want to study, but if you get up close to it, your tether that kind of follows exactly where the robot goes, and then you're pulling it back, it can get wrapped around this stuff. So we had to you kind of get in there and you try to imagine, okay, we got this way and I'm being pulled this direction, and you try to imagine and you try to back it up, and the backup camera is really good for that. Daniel, so in this operation that we did this season, so Daniel has been our kind of tether, in addition to being our electronics engineer, is outside constantly speeding up, slowing down, paying out, pulling back in, right? Francis and I are on the controls, so usually Francis is monitoring robot health and I'm driving, or we'll switch back and forth depending on what's going on, and everyone in here has driven the robot. And so in that scenario, we just go, hey, radio quiet. So we've got radios from the inside to the outside. We're talking over everything. We're like, hey, we're in a really tense situation. I need 100% feedback from Daniel on what the tether's doing. So somebody else at that point in time is usually on or holding the microphone, and so we're talking the whole time about how to do that. And so we've gotten it, Daniel has personally untied it, we've gotten it out of stuck places under ice shelves, we got it out of being stuck in icebergs. The only time we lost it wasn't actually really a thing that was It was unfortunate. We've lost one. Version 3 is a permanent installation in Antarctica, and I will go back for that robot. But that was unfortunate. It got tied around equipment that we asked people to pull out. But the tether can get tied around anything. I have many more stories, but so far we've been really successful, and we practice dead robot recoveries where we don't have any feedback from the robot. We just practice so that we're in a position to hopefully rescue ourselves as much as we can, right? You can't get rid of any of that. But then the other reason that the tether is good, even though it might cost us to lose the robot, is that the data wouldn't exist on the top side. So unlike an AUV, we get all that data back live. So we have it all. So at least we get what we came for, even if it doesn't come back.
We have time for one more question.
I love this presentation. It was amazing. I love the collaborative nature of the work, which lent itself very well to the collaborative nature of how you gave it to us. But I guess, unless you're saving these stories for the bar, because I see polar bear tracks, I wanted to get tell it me like as a movie story. What was the granularity of like each day? Because you said you're going on the 18th. How long will you be there? Yeah. Do the days vary by what you're doing or the modularity of what equipment is going in? Like, what does a day look like, and how many days will you be out there? And tell us about these tracks.
Yeah, so great. Those are an amazing question. So early on, first week, we're just building stuff. We're getting stuff ready to pull out into the field. You saw that this robot is modular. We actually have, so we actually can check it on, we know exactly, like Delta and everyone else, right? 70 pounds is the maximum weight you can show up with 10 of them per person, but it must be 70 pounds. So every piece of this robot can go into a Pelican case that's in that room, and each of them will weigh between 65 and 69 to 70 pounds, and we know that down to, we found a special case for the pressure vessel. The big metal part is the heaviest part. So we have further boxes where, because this comes apart into 7 parts, we then actually build the front half, or the front third, the back third, and those go into 2 boxes, and then the electronics is in its own box as well. So we have fewer pieces to put together in the cold. And then those go onto sleds. We drag those out. In fact, it's almost like we predicted that this would be necessary. So here's what it looks like to drive out during the day. So this is us taking a beautiful snowmobile ride out across the sea ice, and you'll see the snowmobiles and sleds, and so everyone gets up and everybody's having breakfast by 7:30, and then we usually probably leave around 9 if we are lucky. You don't want to go much before that because it's so damn cold. So usually maybe 10 even. And then depending on the day and the mission, then it might be a little bit different. And so on mission days, it's really long. So then we get out there, we're driving between an hour and 2 hours. Then we stop, and it takes us about an hour to 2 hours, probably 3 hours when we first get started, to set camp, to build the robot, to get everything ready. Then we have a dive meeting, just to be like, hey, remember that meeting we had last night about what we're going to do? Does everyone remember it now that we've worked already for 5 hours? Okay, now let's put the robot in. And then we do the missions, which are 3 to 5 to 6 hours, and then we undo all of that. And then we drive back. So those days kill you. They're so long. And we try to get as fast as we can, and we're trying to minimize all of that as much as we possibly can. And if anything is ever dangerous, we just go, right? Wind's gotten terrible, we had that, right? We're just like, this is going badly, we're going in, right? And so that's the kind of thing that we're constantly monitoring for. So then the next day, we're not going outside. People are tired. When we add the microbial analyses, we often have to either do that right when we get home after this very long day, or within about 12 hours of getting back. We have to do the rest of those analyses, or the processing. And then in the early season, we spend a lot of time on analyzing what we just did so that we can get better. So okay, everyone goes around and says, what did we do well? One thing they think we did well, one thing that we can work on at every meeting. And so early season, we'll do that after every dive. So it probably takes us 2 down days before we go back out. And then as we get into the later part of the season, when we got it pretty dialed in, everybody knows what they're doing, we've done it a bunch of times, we're getting faster, we're getting more efficient, we know the science, and then we can also start pushing the science dives because we're not spending our time on the putting it together and taking it back apart because we're getting faster at that. And so we'll kind of push the science requirements as we get closer to the end of the season. And we try to stack the highest priority stuff early, but also the easiest to get stuff, right? So you kind of have this, if we get one mission, we've got this. okay, if we get 2 missions, then we've got this. And then we do the same thing with sampling and all of that other stuff. And so we can also add sampling on some of these days to the whole like long flow. And so everybody's kind of moving or doing something the whole time, which is why then, and then we always take Sundays off, mostly because that's usually a good brunch day. So it seems to be like conservation of brunch is something you can plan on at most organized stations. So that's an important thing. So yeah. That's good.
That's a great question. Thank you, Natalie. So with that, this was a great lecture. Please give them a round of applause. There are more. This is actually a busy kind of 2-week period. I just want to quickly note, if you are a member, Dispatches from the Field online on Wednesday. Michael Girard will be presenting about Mexican caves. For the general public, we have another lecture on Wednesday night on conflict photography. It's open to the public. It's not technically a public lecture, but it should be good. Saturday, the Explorers Clubs. Elodie Freeman is going to be doing the Explorers Clubs. So we've got little kids that'll be here. Fantastic event. Saturday night, very unusual. There will be a flag return in a public lecture by Justin Fornell. He's amazing. And one of the things he's going to be talking about was he swam from Ellesmere Island to Greenland, right in the same space that you learned about tonight. And then next week, there will be no public lecture next Monday because it's actually going to occur on Thursday. Steve Thomas of This Old House is going to be presenting on celestial navigation and a year that he spent as an apprentice in Micronesia learning it. Should be a fantastic event. But tonight is not over. If the robots obviously here, I know you're eager to see it. If we could push any of them down to the bar, normally I try to pull the speaker down to the bar. Please move down to the bar. One of my fellow directors, Mikkel Vestergaard Fransen, he likes to say that more expeditions have been planned at the bar downstairs than anywhere else. Your support at the bar helps support this club, helps us keep the heat on. If you buy more, maybe we can turn the heat up next time. But I just want to close by saying how special tonight was for me personally. The Explorers Club has connected me to so many good people, and a lot of you are here in this room tonight. But it's also brought me to Greenland. It was in a bar after an Explorers Club event where Britney asked me, could you shoot a polar bear? And I didn't know where she was going with this. The Explorers Club brought me to Greenland. More importantly, it brought me into this team. And it's so special tonight to have this team now come to the Explorers Club. Thank you for coming tonight. Thank you to all of you for being here at this tonight. And please continue to mingle down at the bar. Thank you.